All right, so we start in today's derivative practice with this one. This is actually an equation you've seen before. Perhaps you remember, perhaps not. But we haven't ever found the derivative of it at x equals pi. So what I'd like you to do is go ahead and find that derivative and then figure out what would the derivative equal at x equals pi, please. All right, so when you first just find the derivative, notice we are having to use implicit differentiation here. And so we get to this point. Now we can go ahead and start trying to solve it out from there, right? So go ahead and solve it for y prime next. So we go ahead and divide both sides by negative sine of y. And so we end up with negative cosine of x over sine of y equals y prime. We now need to be able to figure out what the derivative is at x equals pi, right? Well, of course, part of that's pretty easy. That just means plugging pi in here for cosine. Okay, but what about on the bottom? What's going to get plugged in on the bottom? All right, so notice there's actually a few different ways you go about it, but yeah, a nice efficient one would be taking our pi and plugging it in for x up here in our original equation to figure out then what the y would be. So I'm going to go ahead and do sine of pi equals cosine of y. And I'm going to now have to figure out what would that y value be. Yes, sine of pi is a value that you should know because if like we're looking at a unit circle, pi, remember, is going straight to the left. Sine of that value, that's how far we're going up, remember, for sine. We're not going up at all, so then sine of pi must be 0. So we're going to go 0 equals cosine of y. And so now we need to know cosine of what equals 0. All right, so we now need to know what cosine of what equals 0. And again, if we think of our unit circle here, cosine, that's how far we're going over. So if cosine is going to be 0, we need to look when it's going straight up and when it's going straight down. And of course, it can loop around, right? And so here y could equal pi over 2. But that's just the first value. Remember that technically it would be plus pi k, where k is an integer. For our purposes in this problem, I think I'm going to just have to stick with the pi over 2. We're going to have to see what happens. So let's actually plug in now and see what we're going to get here. So we're going to do cosine of pi over, I'm going to keep that negative out front, sine of, and technically it's the whole pi over 2 plus pi k, but I'm going to go ahead and just do it with the pi over 2 for the moment, equals y prime. All right, so now we can actually find those values. All right, so then cosine of pi, again, hopefully you know off the top of your head, we're going straight to the left, so cosine there is going to be negative 1. Over sine of pi over 2, we're going straight up. Sine is how far we go up, so that's a positive 1. Oops, remember the equal sign. And so then a negative 1 over 1, so that'd be negative 1, which is positive 1. So y prime then equals 1. All that to find out that the slope equaled 1. But that's not the only possible answer. Because remember that y actually equaled pi over 2 plus pi k. So for instance then, another possibility for what y would equal, we started by checking the pi over 2. Another one would be 3 pi over 2, which is actually going to give us a different answer if we check 3 pi over 2. Because if I now check 3 pi over 2, so I'm now going to make this into 3 pi over 2 instead. What is the sign of 3 pi over 2? Yeah, negative 1. And so then that's a negative 1, which means then that y prime would equal negative 1. So there's two answers. What if I looped it around again and I look for another coterminal angle? So after pi over 2 and after 3 pi over 2, next up would come 5 pi over 2. Is that going to give me a different answer there? Well, if I plug in 5 pi over 2 down here, well, that's coterminal with pi over 2. So that's in the exact same place. So that would actually have the same sign value. And so that would actually give me the only one. So actually what we can then figure out then is that these two, 1 and negative 1, are actually both answers, but they are both the only two answers. So at any given point in this problem, the derivative must equal either 1 or negative 1. All right, so having seen that, I mentioned at the very start of this that you had actually seen this equation before. Do you remember where? Yep, this was off of that implicit graphs packet that we did at the very start when we first saw implicit equations, and we were looking at it going, what the heck do these graphs look like? There were some scary looking graphs, right? And this, to me, is one of the more entertaining of them, because you wouldn't necessarily expect, just from looking at sine of x equals cosine of y, to see a bunch of straight lines. And yet, that's exactly what it gave us. And we can even be very specific. In this case, if I look over here at pi, you can see what we were just looking at. Here, that was the pi over 2 value. Here was our 3 pi over 2. And so you notice it was our positive 1 and our negative 1, but then that it's just going to keep repeating the exact same pattern every time we go up pi. Now, for an extra little bit of adventure here, I would suggest that if you want to kind of push yourself a little bit further, remember we found that y prime equal to negative sine of, sorry, not sine, cosine of x over sine of y. Somehow, I should be able to just boil that down and make it into y prime equals plus or minus 1, right? So, you know, if you want to be able to push yourself just with your thinking a little bit, we're not going to do this together here, but if you want to kind of push your mathematical thinking a bit, think about why and how would this become that? All right, having done that, I'd like to do another one that's kind of similar, where we have another equation, kind of similar. It's got the sines and cosines again. This time I'd like you to please find the derivative at x equals 0. All right, so finding this derivative, which rule do we need in order to be able to find this derivative? Well, notice here that it is y sine of x. In other words, that is y times sine of x. Which rule does that mean we're going to be using? Yes, product rule. You must use product rule here. On the right side, do we also need product rule? Yes, you do. Oftentimes we overlook product rule. It becomes almost a blind spot for some people. So that's why I really want to make sure to call that out there. All right, so once you use product rule on both sides, this is where you're sitting. And now you're at that point where you got to solve for y prime. And I went ahead and simplified it before doing all of that manipulation. That way I'm not doing two things at once. All right, so I moved my y primes all to the left side, and moved my non-y prime terms to the right side. Now that I've done that, I can now factor y prime out of that left side. And so when you just get down to your derivative, down to y prime, this is what we're looking at. But remember, we're not done at this point. We still have to figure out what is the derivative at x equals 0. All right, so when I just plug in the 0, I can see that part of this is going to simplify out quite a bit, right? Because as I'm taking a look at this, the cosine of 0, I can actually know that value, right? What's cosine of 0? 1. Yep, so that's going to become a 1 there. What's the sine of 0 going to be? 0. And then over here we have 0 times sine of y, which is going to be 0. All right, so without even yet figuring out what the cosine part is going to be and what y would equal in this particular case, we get down to finding out that y prime equals, well, let's see here, that would be cosine of y minus y over 0. What does that mean? Well, the divided by 0 tells us it doesn't exist, right? So what would we expect graphically to be happening close to it? Well, it has to be some sort of a discontinuity. Remember, we talked a lot about discontinuities earlier in the year, and there were a few particular different types of them. What was one type of discontinuity that we saw when we were looking at discontinuities way back when? Yep, could be a hole. What's another type? Yep, there were jumps. And what was the other type? Because there were 3 of them. No. Because bounce, it is a point where it's not, where we're not able to take a derivative, but it would be continuous there at least. Although you're right that a bounce would actually be a place where we couldn't take the derivative. In fact, I kind of like including that for this purpose, now that I think about it a little bit more. Yeah. Yeah. And then there's the asymptote. All right. And so then one of those must be going on here. And so then, again, this is actually an equation that you had seen before. It was this crazy looking graph way back when. And so this was the graph of the original. So we found the derivative at x equals 0. What is happening at x equals 0? Well, it may be a little bit hard to tell, but you'll notice there is this strip of blue overlapping the y-axis, right? And so that is actually the cause of our issue. Is that a jump, an asymptote? What's actually happening there? Do we have enough information? No, we would need a little bit more information there. But yes, we got a little bit of a problem there where we cannot take the derivative. That's what's happening. That's what I'm wanting you to see. In this case, the derivative, of course, means slope, right? What's the slope at 0? The slope at x equals 0 here would be undefined. Notice it's basically vertical here. And so because of that, it would actually be an undefined kind of a slope. But I'm wanting to show you that and bring it back because it's been a little while since we've talked about things like discontinuities and points where it's not differentiable, and I kind of want to remind us of that. And plus, it's good practice being able to get there. All right, so I also want to go back and I want to practice finding tangent and normal line equations. So you got your equation here. I'd like you to please go ahead and find the equation of the tangent line and the equation of the normal line here. All right, so first thing, anytime we're going to be writing the equation of the tangent line or the normal line is we have to find the derivative, which then is the equation for finding the slope of the tangent line. So now that I have my derivative equation, I can now go ahead and figure out what the slope is at our point here of 0, 1. All right, so notice then we're going to be doing sine of 0. What is the sine of 0? It is 0. And so then this whole term here becomes 0. Therefore, slope equals 1. Now remember, that slope is the slope of the tangent line. So then to find the tangent line equation, I'm just going to go ahead and actually let's go ahead and label that as tangent here. We're going to go ahead and do y equals the mx plus b thing, right? So I'm going to grab my y value, which is 1, equals the slope of 1 times the x value, which is 0, plus b. Therefore, b equals 1. And so y equals x plus 1. And we're done with the tangent line. Next up, we now need to do it for the normal line. Okay, so for the normal, what is my slope going to be in this case? My point's the same, but what's my slope going to be? Yep, -1. Because remember, the slope of the normal line is the opposite reciprocal. So opposite means flip the sign, reciprocal means flip the fraction, so that's why it's the -1. Although in this case, I'm multiplying it by 0. So that really doesn't change much, does it? And so then, I end up finding that y equals -x plus 1. The only thing that it changed was it changed the slope that was written right there into a negative. But same y-intercept, which tells you that they happen to also cross right at the y-axis. I don't want to forget about our logarithm derivatives, so we'll make this our last practice problem of the day. Please find the derivative of this equation. All right, so for finding our derivative, the derivative of natural log, remember, is 1 over x. So in this case, it's going to be 1 over x squared plus 1. Then it's going to be times the derivative of that inner function, because we're using chain rule here. So that's going to be then times 2x. So if I then take that 2x and I put it on top, it's going to be 2x over x squared plus 1. Is there any other simplifying or reducing that I can do here? No, there is no other simplifying we can do, so this one is done. One little slight caveat to this. What is the derivative of this function when x equals -10? Well, we would take that -10 and we'd plug it in for x, right? So we'd do like 2 times -10 over -10 squared plus 1, so that would give me a -20 over 100 plus 1, so that would be 101. So -20 over 101. Cool. Does that work in here as well? If I plug -10 into the original function, do I get an answer? I want you thinking that through. Really, think that through. Will you get an answer? Exactly. Yes, we will, but only because I'd be doing the -10 squared. If that weren't squared in there, it wouldn't make it a positive. And can we do the natural log of a negative number? No. And so do realize we haven't talked a lot about domain restrictions on these, but it is very possible that when we get into some of these logarithms that there will be domain restrictions. So just kind of keep that in mind as you're going through these.